That's crazy. Yeah. All right. So there's a big thing that happens a lot in mathematics where we want to solve the easier version of a problem when possible. Okay, easy problems are great because they're easy, and especially when you get an easy problem that can be used to solve a hard problem. So essentially, it's not really a hard problem so long as you have the ability to transfer the perspective over to the easier problem. So what we'll do is before we actually get to the definition, I'm going to walk you through why this definition even exists in the first place. Because if we can make that tie, and Samuel already kind of made a tie between the superposition principle at the end of last lecture and what we'll do today. So the first thing is, there's a really, really nice way to take matrix multiplication. So if I had some sort of a matrix like this, maybe 3, 1, 0, 2, 2, 2, 4, minus 1, minus 2, and I multiply this, let's test 3 vectors, okay? The first vector, 1, 0, 0, okay? Now, if I do this, immediately, this should make life really, really easy, because from what we understand in the way the vector equation works, is each one of these vector entries is going to multiply against each one of these column vectors. Now, there's only one entry in here that's going to have a non-zero value, and it's this 1. In other words, I want this 1 to be the entry that multiplies against its corresponding column. So I will have 1 times the first column, which is 3, 1, 0. And then I consider, okay, if I take 0 and multiply it by anything, it's going to give me what? 0. Okay, so 0 times the second column vector is just going to spit out all zeros, so that's not going to contribute anything. What about this next 0? What's going to happen to the third column? It's only going to go to 0. So really, the only thing that survives is just this 3, 1, 0. Okay. Now, suppose I hadn't done 1, 0, 0. Suppose I had done instead, so pretend like I rewrote this. I'm not going to waste the time, but this is rewritten at here. 0, 1, 0. Okay, so now, I switched off, essentially, if you want to think about this in a computer science sense, I switched off the first column, and which column did I turn on? Yeah, I turned on the second. So, what should this computation, you could do this really, really fast. What is it going to be? Yeah, it's just this second column. Okay, so now what if I turn off that switch and I choose 0, 0, 1? What effectively am I doing?
So you're basically getting the weights of the x.
Yeah, so it only is going to switch on now the last column. So if we ever had to solve some sort of a problem or do some sort of computation, wouldn't it be really, really convenient if we could think about a matrix in terms of just these very, very simple vectors, thinking about turning on the columns. And now, look that they're all stacked out together. If I then assembled each of these vectors together and rearranged them back in a matrix, well, I just returned back the matrix itself. Yeah? Okay. So we're going to exploit the nature of these types of vectors. Anything where it's all a stack of zeros except for one entry, and one of those entries is just going to be 1, effectively telling you which column to switch on, and that's going to spit out whatever respective column we have. Okay? Does that make sense? So now, keep this in your back of your mind when we move forward. So now suppose, recall from way back, that if I tell you that a vector x is in Rn, then that's effectively me saying that this has n entries, right? So this is the same thing as x can be represented as having, starting at x1 and going down to xn. So there's n entries in that vector. And why am I returning to this? Because that's pretty basic. We've done that a lot. Well, it's because we're going to do a perspective switch. So consider the following. If I can say that x is in Rn, and that tells me that x can be written then as, well, actually, I should probably choose something concrete so we can do numbers for you. I'll switch this to numbers. So let's consider R3 so that it's easy to write on note paper. So x is in R3, we'll do 3 entries in a vector. This tells me that if I want to think about my vector x as a column vector, what should I list here?
3 numbers.
Yeah, so we got x1, x2, and x3. So we got 3 numbers, 3 entries. Now, when we were splitting up these kind of, when we were doing the vector equations or parametric solution description, we can split this up. Technically, we have 3 separate variables. I'm going to have all the x1s over here, so I have 1 times x1 plus 0 x2s and no x3s. Okay, how many x1s am I getting from x2?
0.
None, so I have 0 x1s. How many x2? Well, it's just x2. And then how many x3? Okay, so what's the bottom one going to look like?
0x1 plus 0x2 plus x3.
Now, why am I going through all of this? Why is that really tedious? Well, because now, remember, we can split this up into separate vectors. So I could think of this as x1, 0x1, 0x1, plus 0x2, x2, 0x2, plus 0x3, 0x3, x3. So far, so good. Okay. Again, why does this matter? Let's factor and see what happens when I factor. Take out that x1. What do I get?
1, 0, 0.
Plus, okay, what's the next one?
0, 0.
Yeah, so x2, take the x2 out, and then you have 0, 1, 0. Plus x3 times, what is that one?
0, 1.
Huh. Look a little bit familiar? What did we just extract out of our perspective of this vector? We just extracted out the very types of vectors that we know are remarkably easy to think about our matrices. Yes? So the key here is we're going to start calling these E. So the convention now, so if it's E with a subscript, this is going to start being a notational convention. So this specific type of vector we're going to call E1. Induct a little bit. What are we going to call this one? E2. And then what about the last one here? E3. Okay. Do we need to see another example with a different value here, or does this make sense? You want to see another example?
No, it's just another question related to that 1, 0, 0 form.
Yes.
Is that why on the reduced echelon form we clear out what is under and over the 1 pivot column?
I see. Yeah. Okay. I see what you're asking. Technically speaking, when we're thinking about that row reduction algorithm, we're not doing it because of this decomposition. This decomposition happens to correspond simply with an identity matrix, which happens to correspond with if you have a square coefficient matrix that you reduce and it goes out perfectly. But so motivation-wise, no, they're not related. Ultimately, like the end form and the perspective switch, yeah, you can make that perspective switch. So it's really up to you. But yeah, when you're doing a row reduction, you're not doing it because of the E1 through E3. It just so happens to coincide that the end product of it will be equivalent perspectives of the same thing. Does that make sense?
Yeah.
I got a question. Does E represent anything in particular? Like, does it have a word or something?
Good question. Yes, I'm introducing you to the notational convention now, so that when we get to the point that we're actually writing out like the definition in words, you're not like, why are we using E? Why are we using this? Why are we using this? So we're doing I'm introducing to you the pieces in your Lego set before the actual instructions, so it's not too overwhelming. Okay. Okay, am I good to erase this? Now, obviously, that was a lot of steps between here and here. You do not have to do that every single time. The idea is we show the reasoning behind what's going on, so that now we can just shortcut from here all the way down to here. Right? So if I said x is in R like 5, then I'm like, okay, well then I'll take my x1, and I know that the vector, the column vector that's multiplying is E1 respective to having 5 entries. So that first one is going to be 1, and then 0, 0, 0, 0. and then it'll be x2. Now I'm going to the second one, so I need to have only the second entry in my vector be switched on to 1, so on and so forth. Does that make sense? Yes.
Is that generally the case?
Yes, that will generalize. So if x's in general are, say, n, then I will have x1 times, and then it'll be 1, 0, 0, 0, 0 down. And then the next one, the 1, is just going to follow the index value. I think there's a magnet in this rag. I can't tell what side's sticking to the board. Okay. Alrighty. Okay, so basically the question is why? This is a question that I don't think you guys in math students are taught to ask very frequently when you do your mathematics, which is the reason why you might get confused if you see a new problem type that doesn't exactly follow what your Pearson example was previously, okay? Learn how to ask a good why question for why you have certain definitions, because motivation is going to inform a procedure far more than just brute force repetition to different types of problems, okay? So let's back it up to a more general case now. Let's talk about, we have a vector now. We're not going to lock down a number of parameters, we'll just call it n. This tells me that I can write my vector x1. Now I'm not going to write the whole stack generally, but I can call this e1, right? I know whatever number of parameters this is still going to be my respective e1, plus and so on and so forth. It'd be x2, e2, and depending on how many I have, I go all the way to xn, e sub what? En, yeah. Okay? And this is a vector equation. And so now what I'm going to do is I'm going to take, I think I made a mistake. Whoopsie. Okay. What I meant to do was I meant to put the vector x before, so just shift it over in your notes like a little bit. So this is saying I can represent the vector x as x1 e1 plus xn en. Okay, sorry about that. Does this make sense? So I'm trying to say, if I say that x is in Rn, then I could equivalently think of x as itself a vector equation with these e's. And so then if I want to think about taking a transformation, linear transformation of this, then I'm transforming both sides, x1, e1 plus so on and so forth. And then we did the superposition principle. What did that did we work through the proof for this? I think we did. Where you can separate out your constant and then have this. So this comes down to being tx is x1 times t e1. So I'm splitting the constant out and having it isolated for every single one, respectively. So if this doesn't look familiar, review in your notes where you wrote down superposition principle. And that's, you can anchor yourself back to last lecture there. Okay, and then I paid off Samuel to ask the transition question at the end of last lecture about, okay, well gee, we're back at the concept of having a vector equation, and didn't we spend a whole bunch of time saying, what if I wanted to write a vector equation as then a matrix equation? So then I could do that. I could say that my t of x is equal to, so essentially all of these scalars are forming the vector, and then each one of these vectors, they are columns of the matrix, and so I can make a matrix that has columns, these column vectors, t of e. So I start at t of e1, and I go down the way until I finish at the last column here, t-e-n. And I'm multiplying this by all of these respective x1 through xn. And now suddenly, we're in business talking about a matrix equation, because this right here can be thought of as the A for a linear transformation t of x is equal to a x. Okay, let's So let's recap so we're all on the same page together. So we have some vector x that has n entries. That means I can write that vector as this linear combination putting x1 times this e1. Why did that work? Well, because we broke it down in an example case so we can see why we are allowed to assume that. And that's going to be the case all the way down to how many entries we have. If I then take a linear transformation of both sides, what we covered in the last lecture is that, well, this, if it's linear, has two properties that allows me to take advantage of the superposition principle. So I can think of this t as being expressed now as this separating out the x1s and then having the t of e1 all the way down as these vectors. And then all we're doing is saying, let's switch now our perspective back and say, sure, those are vectors. Now I want to think of specifically the column of a matrix, organize those columns together, organize together the entries they're multiplied by, and then work back to a matrix. Okay? Questions about that?
I have a question about kind of
Okay.
definition. So, how would this differ if it was instead of x1, x2, x3 like below each other? If it was x1, 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 how would that be represented in terms of x and e as well?
I see the question. Okay, so to state that x is in R3, I'm stating that I have a vector with 3 components.
Yes.
So in general speaking, in general terms, I'm always going to represent a general vector x in R3, where this is the first entry, second entry, third entry. So x1, x2, and x3 here are the placeholders for those entries, not like, yes, you could have them being equal to the same scalar amounts. So you could have something like 7, 7, 7, where they all happen to coincide, but I need to be able to accommodate all possibilities of vectors x in R3.
Okay.
So that's why that's the reason why it's notated.
Okay.
Yeah, it's like a placeholder. Yeah. Anything else for this? So you feel like you could construct this if I had you take a really random spontaneous pop quiz like in 30 seconds? Okay, questions now?
If it was still
Easy
bored.
math.
Okay, cool. So this is the definition that is going to be really, really fundamental. Because now, if we understand where we're getting this from, you will be able to construct for yourself the definition of these standard matrices. So let's put that to writing. Also, just a quick side note on style and organization. Look how neat this is. Okay, that's really easy to read, isn't it? It would be a shame if you were able to see a proof that was really easy to read, and then go on to not do that on your own exams later on in this course. Okay, so I'm trying to mimic as much as possible with the way I handwrite notes what good style looks like. Good style that should be emulated, good style that should be mimicked, okay? I might have to fire this class and get a different. Okay. We're going to call this A right here. This A is a standard matrix for the linear transformation T. And this is kind of, and the entire thing is in itself a definition. So if you're asked about standard matrices, what are they talking about? Well, they're talking about a matrix where every single one of the columns in a matrix is essentially found by transforming those really, really easy E vectors. Okay? So if you have a specific transformation and you want to build its standard matrix, well, just take the really, really easy versions of those vectors, and those are the only vectors you really need to compute to generate what that matrix is supposed to be, because each one of those is in itself a column. So here is kind of an important summary here. So given a linear transformation, T of x is equal to AX. The jth, so this is going to function like an index, the jth column, which I'm going to put this here because this will tie back to a notation you're familiar with, so column vector convention notation. The jth column AJ of the matrix A can be thought of as simply the vector that results from using the transformation T, so using T to transform E sub j, where this is going to be a column vector that has all zeros, except for in the jth entry, which will be the one. That is AJ, so the jth column vector is the same thing as if I use my transformation to transform this vector. Okay? So, I know some people enjoy the words written out. This makes more sense. Some people enjoy this. This makes way more sense than all the words. I don't really care which one makes more sense. Just know what the definition is. Okay? So here's a theorem. Let T take Rn Rm be a linear transformation. So be a linear transformation. Then, do we remember what this symbol means? There exists. Yes, I'm actually going to start a new line because there's going to be a bunch of stuff in a row. It means there exists. Then if I put an exclamation point after it, a unique. So there exists a unique matrix A, such that, so colon is such that T of x, so if I transform a vector x and I define that with AX for all vectors x in R, okay, which one am I putting here, N or M? N. Why is it N? Because I need it to be defined here.
Scott, what's the exclamation point mean?
Oh yes, there exists a unique matrix A such that T of x, my transformation of vector x, it can be written as AX for any of the vectors x I choose in Rn. What is this line of math really trying to communicate? What it's trying to communicate is that there is going to be only one of these per linear transformation. Every single linear transformation is unique. That's kind of part of what it means in the definition for it to be a linear transformation. But the idea is, knowing that it's unique means finding that if you find a standard matrix for a transformation, you found the standard matrix for that transformation. You don't have to worry about there being some other representation out there. So when you take your E1 through En and you transform it under your linear transformation to spit out those columns that form that matrix A, that's going to be a unique matrix, and there's only one matrix that's going to describe that transformation like that. Does that make sense? Okay, so this is a statement of uniqueness. So let's read this together. There exists a unique matrix A such that transformation of x is equal to AX for all x in Rn. let's see here. A is the m by n matrix. And how do I know that it's an m by n matrix? Where am I getting this information from?
From the
Yeah. Okay, so how am I getting it off of here? How many rows? M rows. The rows come from the second one, and the columns come from the first one. A is the m by n matrix, whose jth column is the vector T of E sub j, where, and now I think it was Denzel asked earlier, like more specifically, can I have a more concrete definition of what I mean by this E? Yes, here it is, where E sub j is the jth column of the identity matrix with n, the n by n identity matrix. So that means I can say A is the matrix TE1, TEN. Okay. And I'm going to actually explain this a little bit more because I'm realizing now that might not make 100% sense right away. So recall that the identity matrix, so say, let's do an example, because it's hard to notate generally. So if I take the identity matrix of 5, okay, so that's going to be 1, 0, 0, 0, 0, so 1, 2, 3, 4, 5 rows, and then it's going to have 5 columns. What's the next one? What's the next column going to be?
0, 1.
What's the next column going to be?
0, 0, 0.
Next one? And last one. Okay, so the way what we're saying by what specifically do I mean by these EJs, we can always anchor them down by take the respective identity matrix, and then now these are the conventional special names we're giving to the columns of the identity matrix. So if we needed that, kind of just solidify that definition so that it doesn't feel like we made something up for convenience sake. Notice here that earlier, if you flip back in your notes, when we did the E1, E2, and E3, they only had 3 components each. So that's why I didn't want to be hasty in giving just a flat-out definition of what this E really is, because of its variance. In the same sense that the 0 vector in R2 is represented as 0 as what?
2 entries?
Yeah, 2 entries of 0. But if I said 0 vector in R7, then what am I really saying? It's 7 entries of 0. 0, 0, 0, 0, 3, 4, no. Okay, are these two the same?
No.
They're not the same. 2 entries is very not the same as 7 entries. Okay, these vectors live in different spaces. Now granted, they're both still the 0 vector respectively, but that's how we need to think of these E's. Okay? So if you see, like, say for example, E3, that does not necessarily mean it has to be only 0, 0, 1 in the 3rd spot. Okay? Because if I'm dealing with vectors that exist in like R10, then yes, it's still going to be in the 3rd spot, but then there's going to be 7 more zeros underneath it, completely different vector. Okay, so does it make sense why I didn't want to rush into defining this before we had the chance to see this? Because then you'd have a wrong idea of what these are really representing. Okay, so think of these, put them in the same mental abstract category as how we have to abstract our notation for the 0 vector, as accommodating what space that we are occupying. Thumbs up if that's good. Okay. Sweet. Alrighty, a few more things. Okay. Thankfully, that was the most important topic for this section, so glad that we spent the time on it. it's worth spending the time on it. I remember when I was teaching Calc 3, and I used to wear my Fitbit on my right hand, I would get so many steps from just erasing the board in the lecture. Now you might be wondering, but Scott, we didn't do any examples with the standard matrix. Well, A, you have Pearson, and B, you have a textbook, and C, if you really, really understand the definition, you're going to have a far less horrible time solving the problems in your homework, okay? Because if I had just, imagine I had just written that definition down and said, all right, we're doing a problem with this. This doesn't make any sense, okay? Why we had that, no idea. Motivation, absolutely no idea. I'm just told to know that that's a thing, then suddenly now I have to interact more abstractly with it. Doesn't work, okay? So now that you have the definition, now you have an opportunity to wrestle with some of these problems, and you can know where every single component comes from. If you know where every single component comes from, if you have the ability to reframe a math question in terms of its definitional components, you're gonna be fine, okay? And if you're not, I have an email address, and I have an office hour. I'm not gonna spend too much time on this specific thing, but I will list it. One immediate consequence in practicality for being able to represent with standard matrices is it's going to make our geometric linear transformations in the plane much simpler to think about. So geometric linear transformations of R2. What I'm not going to do is just copy down all of the formulas and pictures that you have access to in a textbook, but I will categorize them all, and there are 4 important categories here. So we can do reflections, we can do contractions, and really, or expansions. I mean, they're related by the constant multiplier. So I think of them as the same family. And then shears, we actually did look at shears a few lectures ago, and then projections, which is flattening something onto an axis. So either the x1 or the x2 axis. So again, if you want little cutesy pictures with a goldfish or a koi fish in the textbook, they have those for you. A, I cannot draw a koi fish, and B, that would waste too much time that doesn't really matter. Okay, make sense? So if you want to see the pictures, you paid for the book, so they're in there. Okay, we need to talk about something really important in algebra. So these concepts of onto and one-to-one. And I know that you've heard of one-to-one before because you presumably had to pass Algebra 1. But onto, we don't really talk about that as much. So a mapping P, Rn to Rm is, we classify it as onto. Okay, this is what we're defining. Onto Rm. If and only if, and then there's going to be a bunch of math symbols here, so I'll walk you through it. For all vectors B in Rm, there is going to exist some vector x in Rn such that T of x is equal to that B. Okay, what is this really saying? Let's first just figure out what the symbols are. Once we get to the symbols, then conceptually it'll make more sense. So I'm saying that this map is mapping this space onto this space, if it's going to satisfy this condition. I need this to be true for every single possible B that I could choose that exists inside of this space. Okay, so that's the first thing. All that this statement is clarifying is that I need this to hold for every single possible thing in the set that I'm going into, okay? If it doesn't work for all of them, too bad, okay? Then, for all of these, now that I know that it needs to be true for every single possible vector that I could find in this space, then I can go back and find, so there exists, I can essentially go back and find the vector x in N. That's just specifying that it's coming from the domain. I can find something in the domain such that if I use that, that's kind of like the key to get into and spit out B. So no matter what vector I choose over here, there's going to exist a vector in the input that gets me to that vector. Does that make sense? I'm going to draw a little diagram here. Think of this space as Rn. Think of this space as Rm. So anything in these places, these are representing the vectors in there. And then T is going to be this relation between them. So to be onto, another way of thinking about it is, if there is an element over here, it has to in some way be linked and related to something in the domain. It has to. Every single one of these needs to be accounted for. So say I relate it like this, and I account for almost all of them, but I don't account for all of them. Is this onto? And then think about just the intuitive notion in the English language, like to be onto something. No, it's not. Why? Because I can find vectors in Rn that do not have a counterpart in the domain. Because there exist vectors over here that are not accessed by vectors over here, this map is not onto. Okay? Compare that now to this map. If I had Rn, T, suppose I'll simplify it so that I can actually draw it. So these dots represent vectors. Suppose I had a map like this. Okay? Is this map taking Rn onto Rn? Yes. How do I know that? Because no matter what element I choose, excuse me, no matter what vector I choose over here, I always can link it back to some counterpart in the domain that gets me there. Yes.
Does that still work if Rn has more dots?
Yeah. It doesn't matter because I could throw in a few more guys in here. And so long as they're going to map, still covers everything. Onto doesn't care the number of elements that are in our domain. Onto simply cares, do they at least make sure we have covered every single element over in our codomain? Now think back, flip back if you have to in your notes. How do we define range, and how do we distinguish that from the codomain? Well, the range was simply all of the possible vectors you could get in the codomain, where the codomain was just, boom, this is every single possibility. So really what we're saying, if we're on to, is I'm saying I need my range to actually just be the codomain. I need my range to actually cover every single possible vector in the space that I'm going into. So the range will coincide with the domain. So that's another thing you can think about for onto. Ooh, that's a terrible star. Is that the range and the codomain are equal to each other. Okay, does this make sense? It's okay if not, because I know that this is the new vocabulary term, and I know it's not very familiar.
Is the element in Rn and the element in Rm, they're equivalent, like they're the same? What does it mean? Like they just means they have a relationship, or they're almost the same? I mean, the element, the dot in Rn is completely the same as the dot in Rn.
Oh, I see the question. Yeah. So the dots are just meant to represent like an object abstractly. So it's not an actual an equivalence. So this is not about equivalence between two sets. This is about whether or not there can exist some sort of relationship between two things.
What does the relationship mean? Like addition or like
Through the transformation T. Oh, you know what? I'm gonna write down an example that's gonna help.
Yeah. This example will help.
Yeah. I actually really like this example because it's familiar, and then it helps us move the terminology over a little bit more, a little smoother. So, recall back. So say I defined a function that took real numbers to real numbers, and I define it by a quadratic. So f of x is equal to x squared. So visually, when I'm thinking about this, this is the set of real numbers, this is the set of real numbers. And so I ask myself, okay, is this mapping R onto R? Is this particular function, is this particular mapping, so to speak, onto? And so the question I say is, okay, if it is, then for every single element I find in the codomain, I need to be able to find the counterpart over here. So say I chose, say I chose 4. So I'm choosing the element 4 in the codomain. Can I find an element in my domain that lets me spit this out? Which element? 2. Drawn to scale. Okay. But now say I chose the element in R, -3. Is it possible for me to take a real number, transform that real number, and spit out num -3?
No.
That's impossible, okay? And so, because of that's impossible, I've now found an element in my codomain that cannot be accessed by my rule, by my map. Ergo, this is no longer onto because I have failed to give everybody essentially an element from which they can come. Compare that with a line. Okay, so suppose this is g of x is equal to x minus 1. Okay, so now, is it even possible for me to find a real value number that I couldn't access or find from the domain? No. Another way I could frame that with different, more familiar terminology. Is the range of this line g equal to all of the real numbers? Now, if this real numbers, if that's the codomain, is the range of this mapping equal to the codomain of the map? Yes. And when the range and the codomain coincide, this is onto. Because no matter what value I choose in the codomain, there's always a way to find a domain value that gets me back.
How does it work on matrix? Since this one is function, but we're doing matrix, right?
Right, so this is an example for just abstracting the vocabulary. So then when we're in the context of doing like spaces, these matrix spaces, so like we have vectors Rn to vectors Rm, we're not doing like a graph. So we can't necessarily draw it in a plane or some sort of visual graph like this. We just have to understand that if I took a matrix, so if I defined A like 4, 3, 7, 1, minus 1, 1. If I took a matrix like this, then what type of inputs do I need? How many? I need 3. And these, what type of output is it going to spit out? How many?
2.
The same number as rows. So it's going to spit out some sort of vector y. And so what I'm really doing when I'm taking t of x is equal to ax is I'm saying, okay, I plug in some x, I spit out some corresponding y. Plug in some x, spit out some corresponding y. And eventually the question becomes, am I allowed to choose any vector y and then work backwards and then be guaranteed to find an x that gets me there? That's really the question. Now, obviously, since I just wrote down random numbers, I can't answer this for this specific matrix. But this is really the question of onto. This, we can consider this linear transformation to be onto, so long as no matter what vector I choose over here in R2, I can find the vector here in R3 that will get me there via this matrix.
So is it correct to say that all linear transformations are onto?
No.
No. Okay. Because in this one it was also that's a linear versus nonlinear situation. So I
Don't
know
read
that-
into
okay.
the analogy too much there. This analogy was more for the purpose of the distinguishing between our range and our codomain language.
Okay.
Okay. What we're gonna we'll spend time on this because this is important, and I might talk about it more later. But not every single one is going to be onto, because if every single one was onto, then we wouldn't really be making a separate definition for this property.
If I say there is a free variable in x1, x2, and x3, then I say it's not onto, like, since for each y1 and y2, you cannot find a solution for the variables for x. So it means it's not onto, like you said. For onto means that you can find all solutions for variables. Like you plug the y1 and y2 back, you can find the solution for the variable x. So it means if there is a free variable, then it's not onto.
You're thinking of the theorem. So the reasoning that you're going through in your head, now translating the perspective from instead of just a general y, we did talk about previously, what if I have like in a non-homogeneous system, some vector b, when am I guaranteed to have that unique solution? So yes, that's it. Look in the textbook, there is one of the end theorems for the section is going to articulate the question that you're asking, essentially, and then stating it as a theorem.
Okay, so like if there is like all the variables that exist, then it means it's onto.
I'm gonna make sure I don't say something wrong here because I think I wrote it down. Yeah. So if these columns end up spanning your space, then you're gonna be onto, because to span that means that every single linear combination is accommodated for with whatever you choose here.
Oh, okay.
Yes.
So that means match, right?
The free variables question is going to come into play when we start talking about one-to-one transformations and not necessarily the onto transformations.
But what is the example of not onto?
Oh, not onto?
Yeah.
I cannot throw up the numbers on my own right now. But an example of a not onto transformation is going to be if I have some sort of a matrix that essentially the way that the matrix is written is that it's going to remove access to certain outputs. So essentially, a matrix that's designed or written in a way that irrespective of I could put every single possible vector in here, but the way that it's being transformed is going to restrict certain outputs. Go ahead and when you look in the textbook, look at examples of projections, because what that's going to do is it's going to show you types of matrices that are going to collapse a ton of vectors just onto a very, very restricted output type of vector. And so we're restricting what kind of vector you can get out to only like either flattening it out onto the x1 axis or the x2 axis in R2. So that would be a good case of you can't access every single output vector because of the way that the transformation's operating. So this one is definitionally not onto. So if you want examples of not onto linear transformations, this is going to be a good starting place. Okay, these are good questions. Anything else? Okay, what time is it? I don't want to run over.
204.
Okay, perfect. So I'll write down now the definition of one-to-one, and then we'll be set. If you go on to take higher algebra later, if you need that for either math or something, you will see this definition again. It reappears in a more general sense. Okay. Definition. A mapping T, we're going to take again Rm pretty standard, is 1-to-1. You've learned this before, so let that intuition guide into analogously here what we've got going on. If and only if, well, I'm going to write it like this. If this statement is true. So if I have t of x, if I transform a vector x, and I know that it's equal to me transforming a vector y, the only way that's possible for those to coincide is if those two vectors are actually just the same thing. Okay, what is this saying? Is if I input something into a map, and it ends up being the same thing as inputting another vector through that same map, the only way this is allowed to exist is if, you actually just had the same element the entire time. You can't actually access the same element, you can't access the same output with different vectors. Some classical examples of this, like in what we're familiar with algebra, actually I just had them up, I shouldn't have erased it. A linear equation is a classic example of one-to-one, because to every single output, there is only and precisely one input that gets you there. A parabola, not the case. That's not one-to-one, because pretty much for every single one of the outputs, you can find two inputs that squares you to get that. And some cubics will have some overlap, so if it fails, you can actually find that same value with different types. So one-to-one is going to be the property that we're going to essentially have. If you have a pair, you've only got one pair. This is essentially our mathematically monogamous people, okay? For every single input, only one output. Onto doesn't care about that. Onto you could have.
Onto is Mormon.
That's great. I wasn't gonna say that loud because this is being recorded and it's going on the internet. But you can have. Notice here there were multiple possible elements that cover the same one, but we don't care. It's still onto so long as everything's covered. Okay. So let's do a quick logic test. If I have a set that is 7 elements, and every single one of those 7 elements is going to an element over in the other set, is that necessarily onto or no? So if I have 7 elements, and I have 2 elements, does every single possible mapping have to be onto?
Yeah. Yes.
No. What could happen is all 7 of these decide to pile up on just that one element. So did we accommodate for one of them? Boom, not onto. So definitionally, this is not onto. And if it looks like nuclear launch codes or like doomsday graphics, it's probably not one-to-one either, okay? Now if I had here's the next little common fallacy. If I have the same number of elements in both of my sets, is every single map one-to-one? No. Now this is one-to-one because for every single input, there's only one output. But that's not the only way I could have done that mapping. I could have had something like this, where all of them decide to gang up on just one. Is this onto? Why is it onto?
It is.
Because you can access all the
I love that answer, by the way. No, yeah, it's because every single one every single element over here can be traced back to here. So is this both onto and one-to-one?
Yes.
So this is a really, really well-behaved, nicely structured type of map. This is not part of the course, but you might as well learn some math. We call these bijections. So when it satisfies both of those structures, that map becomes a bijection. Okay. If there are no questions, class is dismissed, and then I'm going to head to my office here. Yes?
If A, the bottom row was all just zeros, was actually not onto an example of it?
Yes. Because if you clear out all zeros, then you've made it impossible to access any vectors that have values in that bottom, because that bottom parameter is going to get nuked up to 0 every single time. So it collapses, yeah. That's a good observation, yes.